Have you ever wondered what travels through the wires of your gadgets every time you switch them on? Let's delve into the world of electric current, the silent yet omnipresent force that illuminates every light bulb and powers every appliance in our homes. Electric current is essentially a flow of charged particles, usually electrons, moving through a conductor like the copper wires in your walls. This flow is what brings our electronic devices to life, from the smallest digital watch to the largest refrigerator. It's like an invisible river of energy, constantly moving beneath the surfaces of our everyday lives. In metals, these charge carriers are electrons, which are negatively charged particles. They travel through the conductor, creating an electric current whenever we connect a device to a power source. This is what lights up our rooms, cooks our food, and yes, even charges our phones. In the next few minutes, we'll uncover the invisible yet powerful force of electric current. At its core, electric current represents a journey, a flow of tiny charged particles. Imagine a bustling highway, but instead of cars, it's charged particles like electrons and ions zooming along. This flow occurs within a variety of materials, through the metallic veins of wires, across the vast expanse of semiconductors, and even through the fluid paths of electrolytes. Electric current is formally defined as the net rate at which electric charge flows through a surface. It's like measuring the volume of water flowing through a hose every second, but instead of water, we're measuring the flow of electric charge. The basic unit of electric current is the ampere, often shortened to amp. 1 ampere is equivalent to the movement of 1 coulomb of charge passing a given point per second. For perspective, a single coulomb equals about 6 quintillion 240 quintillion electrons. That's a 6 followed by 18 zeros. Now let's talk about the movers and shakers in the world of electric current, the charge carriers. In metals like copper or silver, which are common in electrical wiring, the charge carriers are electrons. These electrons are the negatively charged particles that swarm around the positively charged atomic nuclei fixed within the metal lattice. When an electric potential is applied, these electrons drift from one atom to the next, creating a current. In other scenarios, such as in battery electrolytes or neon lights, the charge carriers can be ions. Ions are atoms or molecules that have lost or gained electrons, acquiring an electric charge. In electrolytes, positive and negative ions move in opposite directions to the flow of electrons, contributing to the current in their own unique way. Understanding these fundamentals allows us to harness and manipulate electric current in countless applications, from lighting our homes to powering our gadgets, and even driving the wheels of electric vehicles. So every time you use an electrical device, you're harnessing the power of flowing charges. Now let's dive deeper into how we measure this flow. The ampere. The ampere, often shortened to amp, is the basic unit of electric current in the International System of Units. Simply put, 1 ampere equals the steady flow of 1 coulomb of charge passing a given point in a circuit each second. Think of it as measuring how much electric charge is moving through a wire. To bring this concept home, consider household appliances. A standard LED light bulb, for instance, might draw about 300 milliamps, while a hairdryer can draw up to 10 amperes. This means the hairdryer uses a significantly larger flow of electric charge to operate compared to the light bulb. Measuring this flow is crucial, and that's where an ammeter comes into play. An ammeter is a tool specifically designed to measure the electric current in a circuit. It can be connected in series with a circuit element to directly measure the current flowing through it. The precision of ammeters allows us to understand and manage how much power our electrical devices are consuming and ensure they operate safely and efficiently. Understanding amperes not only helps us use electricity more wisely, but also underpins much of the technology around us. From charging our smartphones to powering our refrigerators, the flow of electric current is integral to our daily lives. With amperes, we can quantify the invisible, making the intangible tangibly useful. From lighting our homes to powering our phones, electric current is a silent helper in numerous tasks. It's hard to overstate the importance of electric currents in our daily lives. They are the unsung heroes in the background, making modern conveniences possible and our world more comfortable and efficient. Electric currents play a pivotal role in generating magnetic fields, which are absolutely crucial in the functioning of motors and generators. Let's delve into this a bit. When electric current flows through a wire, it creates a magnetic field around the wire. This phenomenon is harnessed in electric motors found in everything from household appliances like mixers and vacuum cleaners to electric cars and industrial machinery. In each case, electricity is converted into mechanical energy, allowing physical tasks to be performed with ease. Similarly, generators work on the same principle, but in reverse. They convert mechanical energy into electrical energy. When a coil of wire is spun inside a magnetic field, it induces an electric current in the wire. This is how most of the electricity in our power grids is generated, whether it's from wind turbines, hydroelectric dams, or power plants of various kinds. Another fascinating application of electric currents is in the production of heat, known as joule heating. This principle is at the heart of devices like electric heaters and incandescent light bulbs. In these devices, electric current passes through a material, increasing the energy and temperature of the material's atoms. As these atoms heat up, the material itself heats up, emitting warmth in the case of a heater or light, and warmth in the case of an incandescent bulb. From the warmth that comforts us on a chilly day to the light that brightens our nights, electric currents influence our lives in profound ways. They heat our water, cook our food, and even power the device you're using to listen to this. The effects of electric currents are all around us, energizing our world in ways we often take for granted. Ever wondered why electricians talk about the direction of current differently than scientists? Let's dive into this curious aspect of electricity. In the realm of electrical engineering and everyday discussions, you'll often hear about the conventional current. This term refers to the flow of positive charges from the positive to the negative terminal. Interestingly, this is purely a convention established for simplicity and standardization. However, if we peek into the microscopic world of conductors like wires, the actual scenario involves electrons, which are negatively charged, moving from the negative to the positive terminal. This movement is known as the electron flow, and it occurs in the opposite direction to the conventional current. Why maintain two perspectives? Well, understanding both helps in the analysis of electrical circuits. Engineers use the conventional current for calculations and diagrams, while physicists might focus on electron flow to explain phenomena at the atomic level. This dual perspective on current flow helps professionals accurately design and troubleshoot electrical systems. As we've seen today, electric current is a fundamental aspect of our daily lives. Let's take a moment to recap. Electric current is essentially a flow of charged particles, such as electrons, moving through a conductor. These particles carry energy from one place to another, enabling virtually all electronic devices and systems to function. Diving deeper, the unit of electric current, the ampere, measures how much charge passes a point in a circuit per second. Understanding amperes is crucial because it helps us comprehend the power and capacity of various electrical devices. Whether it's a small battery powering a remote control or a massive current driving an industrial machine, the principles are universally applicable. In everyday life, electric current powers everything from the light bulbs in our homes to the smartphones in our pockets. It's also the force behind more visible technologies like the humming of a refrigerator or the spinning of a washing machine. But the implications of electric current go beyond mere convenience. They are integral to advancements in healthcare, telecommunications, and even transportation. For both consumers and professionals, a solid grasp of how electric currents function can enhance safety, efficiency, and innovation. It encourages informed decisions about energy consumption and electrical appliance maintenance, ensuring that we not only use technology, but also understand it. Next time you flip a switch, remember, you're commanding a powerful flow of tiny charged particles. Electric current, though invisible, impacts our lives profoundly.